Hey, welcome back. It's AP Chemistry, and you're here with Miss Gray. We're going to work on some more IMFs today. Podcast 8.3 is all about phase changes, and of course these are going to be governed by intermolecular forces. So phase changes, of course, is when we change the state of a substance from solid to liquid to gas, or whatever, right? And every time there's a phase change, then we're going to have a change in the amount of energy of our system. So, for instance, the heat of fusion, delta H fuse, describes the enthalpy involved to melt something. The molecules of a solid free up, having more ability to move. So this is basically melting. The same amount of energy would go into freezing the substance, but of course it would be opposite in sign, right? We would have to take the energy away to get it to freeze. The heat of vaporization, of course, describes when the molecules of a liquid completely break free from one another, which is boiling or evaporation. And the heat of vaporization is almost always larger in comparison to the heat of fusion, because to break free of all the IMFs in a substance is greater than only some of the IMFs to give the solid more freedom to move. Other enthalpy changes that I need you to know are, in particular, heat of sublimation, where the molecule goes from a solid to a gas without ever having been a liquid. But the neat thing about heat of sublimation is that it can be determined or derived from the heat of fusion and the heat of vaporization together. If we're churning a solid to a liquid and then a liquid to a gas, it's going to add up to the same amount as going directly from the liquid to the gas, because energy and enthalpy, these are, state changes, state functions, right? Where it's not the pathway that matters, it's just the end result. There you go. So here's an example where we might have to use this kind of information. A 5-gram sample of water is removed from a freezer and heated from an initial temperature of -5 degrees Celsius to a final temperature of 102 degrees Celsius. So we have all of the data that we need to calculate the amount of energy that's been absorbed by water during the whole process. Let's look at phase diagrams. Phase diagrams are a graphical way to summarize the conditions under which equilibria would exist between different states of matter. So what temperature and pressure combination is going to give us an equilibrium between the solid and liquid phase, or the solid and the gas phase for that matter. There's only a certain set of criteria for temperature and pressure combinations that would fit this equilibrium state. It also predicts the phase of any substance at any given temperature and pressure combination. So let's look at a phase diagram. In this phase diagram, you'll notice that we have a line that separates the solid from the liquid. Anywhere along this line represents the equilibrium between solid and liquid equilibrium between the solid and liquid states. Okay? Going across this line is the change that's called melting, right? So as we go higher in pressure, we can see that the melting point changes according to the pressure, but not nearly as much as the boiling point changes according to pressure. So this going from liquid to gas describes boiling. The triple point is the place at which all three phases are in equilibrium. There's only one given temperature and pressure combination at which all three phases can exist at the same time. The critical temperature is the temperature on a phase diagram that's the highest temperature at which a distinct liquid phase can form. Beyond the critical point here, you will no longer be able to have a liquid phase. You would have everything from then on is just a gas. So critical pressure is the pressure then that's required to bring about liquefaction at that critical temperature. So at that highest temperature, how much pressure do you have to keep that liquid together? So something that's nonpolar, that does not have strong IMFs, or something that has a very low molar mass, is going to have low values for the critical temperature and pressure because it's going to tend to pull apart easily into the gas phase. All right, so if we're turning liquids into gases, then we've got to talk about vapor pressure. Vapor pressure is the pressure that's exerted by a vapor or a gas, right, in the space directly above the liquid. All right, so if we have a higher IMF, the higher the intermolecular forces are, the lower the vapor pressure will be, because it doesn't easily turn from a liquid to a gas. It holds together better. And a dynamic equilibrium establishes when we change a gas to liquid. Remember when we were rolling the dice and moving from liquid phase to gas phase? You didn't stay in the gas phase because then you had to roll the dice again, and you could only stay in the gas phase if your number was high enough. If it was too low, then you'd have to go back into the liquid phase, and you just keep going back and forth, right? That's what dynamic equilibrium is. It means not all of the molecules exist as a gas and then just stay as a gas. It's that they turn into a gas, then go back as a liquid, and then they go back to a gas, and so on and so forth. Volatile liquids don't have vapor pressure. These substances have such a high vapor pressure. Sorry, they do have a vapor pressure. They don't have a dynamic equilibrium. Volatile liquids are substances with such a high vapor pressure that the liquids evaporate to dryness without going back into the liquid phase. So no dynamic equilibrium exists for a volatile liquid. That's how we can distinguish whether something is considered to be volatile or not. And if we look at boiling, then we'd see how liquids would boil. When would a liquid boil? It can only boil if the liquid particles can turn into gas particles that can then actually escape from the container. So when the vapor pressure is equal to the external pressure acting on the surface of a liquid, generally coming from the atmosphere, atmospheric pressure, then the liquid's allowed to boil. Remember, in boiling, the bubbles of vapor form within the interior of the liquid. For evaporation, they form at the surface of the liquid, not within the interior. Surface. I'm trying to spell here. So one thing that we would need to be able to do is to adjust for temperature and pressure. Remember the ideal gas law? The Clausius-Clapeyron equation allows us to make predictions about any given liquid based on temperature and pressure combinations. So what you'll do to solve Clausius-Clapeyron equations is you'll draw a graph where we have the 1 over RT is on the x-axis, and then the y-axis is the natural log of the pressure. So that means that the slope, if this is y equals mx plus b form, the slope is the vapor, the enthalpy of vaporization. So the slope of the line that you make in this graph is opposite in sign, but equal in magnitude to your heat of vaporization. And then C, of course, is just some constant that's different for each type of substance. It describes the slope-intercept, right? The intercept of this graph. So the best way to solve things in the Clausius-Clapeyron equation is either to sketch the graph by hand or to use your graphing calculator to come up with an equation of this line, an equation of this straight line, so that we can determine the vapor pressure for that substance. All right, so we're going to work on this in class. We're going to practice this together so you see how it's done. We've got a couple of assignments where you'll get a chance to try this out. Well, guess what? That's it for today. We're going to have more chance to practice these things in class. We're going to need to have your graphing calculators with you. And we're going to keep working on IMS for one more podcast. I'll see you guys soon.